Okay. Good afternoon, everyone. My name is Giannis Nikolentzos. I'm an assistant professor at the University of Peloponnese, and today I will be talking about graph neural networks. So I will start off by giving you a few details about graphs. I'm pretty sure you produce and consume textual data, image data, other types of data on a daily basis, but perhaps some of you are not familiar with graphs. So a graph is just a mathematical structure that we use to represent data, and it consists of some nodes, and some nodes are connected to each other by edges. You can see an example of a graph on the slide. We have 5 nodes in total in this graph, and we have also 6 edges. And typically the nodes represent some entities, while the edges capture interactions between the entities or relationships between the entities. How do we store the graphs in our machines, in some computer? Perhaps the most common representation is the adjacency matrix, A, of a graph, which is an n times n matrix, where n is the number of nodes of the graph, and in position ij of this matrix, we have a non-zero value if the 2 nodes I and j are connected by an edge. Otherwise, the value is equal to 0. And you can see the same graph right here, and this is the adjacency matrix of that graph. You see that we have 5 rows and 5 columns. These rows and columns correspond to the 5 nodes of the graph. And the non-zero values, they represent edges. So this one means that nodes 1 and 2, they are connected by an edge. Graphs arise naturally in a wide variety of domains. For instance, in chemoinformatics, we have molecules, and we can represent molecules as graphs, where nodes correspond to atoms and edges to chemical bonds. In medicine, we have different types of graphs, like brain networks, and also social networks. They are naturally mapped to graphs. For instance, Facebook, you can think of that as a graph where nodes are users, and 2 users are connected by an edge if they are friends on Facebook. And there are, in those settings, there are different problems, estimation problems and prediction problems. We cannot be solved by traditional, conventional algorithms, graph algorithms. So we need to use machine learning techniques to solve those problems. And there are mainly 2 families of methods that we can use. Graph kernels, which were the main approach around a decade ago. And more recently, we typically use graph neural networks, and this talk focuses on those models. And since graphs, they consist of different components, of nodes, of edges, of subgraphs, and so on, we have different problems, like node-level problems, such as node classification and node regression, where we focus on the nodes of the graph. Graph-level problems, where we focus on the entire graph. And we have other tasks, like link prediction and community detection. In this talk, I will focus on the first 2 tasks. I will try now to convince you why we need machine learning algorithms for graphs. And this is a subgraph of some social network. And the nodes represent some users. And in this social network, users are allowed to transfer money to other users. And there are some fraudulent users, in fact 5 of them in this network, that they try to trick benign users and steal their money. And in such kind of networks, we would like to have some model to identify whether a node is fraudulent or not. And for this task, we could use node classification algorithms. So an algorithm that can, given a node, it can tell us whether it's a fraudulent user or a benign user. And this is, of course, a node-level task because we focus on nodes. And I will also give you an example of a graph-level task. Here, you can see some molecules. And we are interested in predicting some quantum mechanical properties of those molecules. In fact, those 12 properties that you can see on the top. And there are for the first 3 molecules, these values for those targets are known. These are those values for the first 3 molecules. And we have some other molecules, like this one on the right, for which those values are unknown, and we need to somehow estimate those values. And to predict those values, we can use graph regression algorithms. So we can train some model that takes these graphs as inputs and some others, and then we can use the model to make predictions for the molecules of the test set. And what is interesting in this setting is that we can, like the traditional approach for estimating those values is to use DFT computations. And those DFT computations are pretty expensive. So we need around 1,000 seconds to estimate the properties of a single molecule. While if we train some machine learning method, like a graph regression algorithm, we need less than 1 second to estimate those values, and with pretty high accuracies. So you might ask, can we just use traditional learning algorithms to solve those node and graph level tasks? For instance, can we just represent each node by the corresponding row of the adjacency matrix and then feed those representations to an MLP and get predictions for the different nodes? We could do that. One problem here is that this matrix is typically very large because we don't have just 4 nodes in real-world networks. We have thousands of nodes in some of them. So each row would be a very long vector. Still, we could represent this as a sparse matrix, so we could use sparse vectors instead of dense like those ones. But another problem that we have here is that these vectors, they only capture first order proximity. And when I say first order proximity, is that for each node, we just know its direct neighbors. So if 2 nodes, they share no common neighbors, the inner product of their embeddings of the vectors is equal to 0, and those nodes are considered totally dissimilar, while in fact they might be pretty similar in some cases. For graph level tasks, there are different approaches that we could use. We could just stack the rows of the adjacency matrix into a vector, and then feed this vector to an MLP again to make predictions. So that would be one approach. We could instead treat this as an image, right? We have a 2-dimensional matrix. So we can think of this as an image and use some convolutional neural network, and then the convolutional neural network will give us some representation for this graph, and then we can use this to make predictions. And a third approach would be to impose some ordering on the nodes. So we could think that this is the first node, this is the second, this is the third, this is the last, and introduce the concept of time and use some recurrent neural network to compute the representation of each graph. However, none of these approaches satisfies one property that we would like to have, and this property is permutation invariance. So what does permutation invariance mean? It means that we can, by applying some permutation on the adjacency matrix of a graph, we obtain, in fact, an identical graph, so a graph that is isomorphic to the input to the original graph. What we actually do is just reordering the nodes, renaming the nodes. And we would like some model to produce the same output for all possible permutations of the input. And this property is not satisfied by these 3 approaches. And I'll give you an example to make this clear. So you see this graph, and this is the adjacency matrix of the graph on the left. And as you can see, the graph on the right is identical, is isomorphic to the one on the left. The difference between those two is in the names of the nodes. So we just have renamed the nodes. So we have just changed the correspondence between the rows of A prime with the different nodes. And in fact, this matrix is a permutation of that matrix. So we would like to have models that can indeed output the same representation for any permutation of the input graph. So this is why people have designed the models that are known as graph neural networks. So these models satisfy that property. And most of these models, they belong to a family that is called message passing neural networks. And these models, they consist of a sequence of message passing layers. And within each message passing layer, we just update the feature vector of its node. So this vector HV is the vector of node V at layer T+1. And here we just focus on node V, and we saw how we update its representation. So you see that we have two operations here, the aggregate operation and the combine operation. And the aggregate operation takes as input a multiset, which is a generalization of a set where we can have multiple elements of multiple identical elements. And this multiset, it contains the vectors of the neighbors of node V. So we have this multiset of the representations of the neighbors, and somehow from that multiset we end up with a vector M of V. And then we combine this vector M of V with the current representation of node V, and we end up with a new representation of node V, and then we can feed this to the next message passing layer, or if this is the last message passing layer, we can have some further layers like MLP layers or linear layers to make some prediction. And what is interesting here is that there is no natural ordering of the neighbors of a given node. So the output of this aggregate function needs to be the same no matter what the ordering of the neighbors is. And so this function aggregate, it has to be permutation invariant. This is an example of one message passing layer of like high-level overview. You see here we focus on the green node 4, and you see that the neighbors of node 4, nodes 2, 3, 5, and 6, they send their feature vectors to node 4, and so node 4 receives this multiset of representations. It applies the function aggregate, and this function outputs a new vector M4, and this is combined with the previous representation of 4, and we get the new representation. I will now present a concrete example of such a model. So this is known as the graph convolutional network. It's one of the most popular GNNs, and it was proposed a few years ago. And in fact, here the aggregate and combine functions, they are merged into a single function. And this is like the formula that we use to update the features of the different nodes. And you see that here on the right, this is the aggregate step of the model, because as you see, we compute the sum of the feature vectors of the neighbors, and those are then combined with the feature vector of the node itself to give us the new representation. This is just a normalization factor. So here D of V is the degree of node V, and we use this to deal with some numerical instabilities like vanishing gradients or exploding gradients. And this, we don't, in practice, we don't just compute the representation of each node separately. This is done simultaneously for all the nodes, and this can be written in matrix form, like we can use this formula right here. And I will now give you an example of how the new node representations are computed. So this is like our input graph. You see that we have 4 nodes, and the nodes are annotated with some features, and those features, they might be features of the users in a social network, or features of the 8 atoms in some molecule, and so on. And we have the adjacency matrix and this matrix X that stores the input features of the nodes. And what we need to do first is, as a pre-processing step, is to compute this matrix A hat, which is like a normalized adjacency matrix, takes into account the degrees of the different nodes. So we can just first compute matrix A hat, and then suppose that W and B, they represent the weight matrix and the bias vector of the first layer of the model. This is how we compute the new node representations. So, and this is a matrix that consists of 4 nodes because the graph contains 4 nodes in total. And by adding a single message passing layer, each node obtains information about its direct neighbors. So it can solve problems that where information about those neighbors is needed. If we add more layers, typically we have 2 or 3 or 4 layers in most cases, but it depends on the application. But if we add more layers, then the node obtains more and more global information about its neighborhood. So the number of layers is somehow connected to the size of the neighborhood that is taken into account into the learned representations. Okay, so as we've seen in the GCN model, we weight the neighbors based on their degrees. But in some problems, some nodes might be more important for some nodes than others. So in this example, you see that node 2 has 3 neighbors, node 1, node 3, and node 4. And in some specific application, node 3 might be more important than the rest of the nodes for that task. And so we would like the model to assign a higher weight to node 3 than to the rest of the nodes. But the GCN model cannot achieve that because of this normalization scheme that it uses. But this was solved by another model, the graph attention network, where here we learn an attention coefficient for each neighbor of a given node. So here you see that we focus on node 1. Node 1 has 5 neighbors, and we also have this self loop. And those coefficients, alpha coefficients, they are attention coefficients. And for instance, if in some task node 4 is more important than the rest of the nodes for that task, we would expect this value to be much larger than the rest of the values. So the learned representation, they depend on the importance of the neighbors. And this is how the node representations are updated. This is a single layer of the model. And you see that here we have those attention coefficients. And again, this can be written in matrix form. And we can even have multiple attention layers. We don't need to have just a single one. And we can somehow combine the outputs of the different attention layers, either concatenating them or computing the average or some other kind of operation. And these two models, the GCN and the GATT model, we can, as I said, we can use them to learn node representations, and then given some node task like node classification, we can add some more layers, fully connected layers, and we can make predictions. And this can be trained end to end. So it's not two different components, it's a single neural network. But I said before that we are interested in some cases to produce graph representations as well, not just node representations. So can we somehow modify those models to produce also a vector that represents the entire graph and not just its node of the graph? The answer here is yes, and it's pretty simple to do that. We can just add a readout pooling function to the model. So here step 1 is what I've already explained. It's the different message passing layers that update the node representations. And once we have added some message passing layer, 2, 3, 4, 5 of them, then we can obtain a vector that represents the entire graph by applying this function, readout function, to this multiset. So this multiset contains the vectors of all the nodes of the graph. And this function, as you might imagine, it needs to be permutation invariant. So no matter what the ordering of the nodes is, the output of this function needs to be the same. In most cases, we can use some very simple readout functions. Here I list 3 of them: the sum function, the min function, and the max function. So we just add those functions to the model, and we obtain a single vector that represents the entire graph. But more sophisticated approaches have also been proposed. And for instance, the diff pool model is inspired by the pooling layers of CNNs. And this model learns hierarchical pooling similar to those of CNNs. And you see that we have in the input some graph, and then somehow we merge nodes of that graph, and we have smaller graphs. So we gradually decrease the size of the graph, and we end up at some point with a single node, and we can use the feature vector of that node to deal with graph level tasks. But how exactly do we merge the nodes? So how do we do this clustering thing here? The trick is to learn some matrix S. So we learn one matrix S at each layer of the model. The matrix S consists of NT rows, where NT is the number of nodes of the current graph, and NT plus 1 columns, where NT plus 1 is smaller than NT, and it's the number of nodes of the new graph that will be produced after the pooling operation. And once we have computed this matrix, we can do these matrix multiplications and get the new matrix of node features and new adjacency matrix of the graph. And how can we learn matrix S? In fact, we can use a message passing neural network, this one, and we apply the softmax function in a row-wise fashion because we want each row to sum up to 1, and the different values, they correspond to soft assignments of the nodes of the current graph to the nodes of the new graph that will be produced at the end of the layer. And I'll give you an example of one layer of this model. So here we have this graph, which consists of 5 nodes, and we have this adjacency matrix. This is the matrix that contains the transformed node features, so the features that you can see on the nodes of the different of the graph. And suppose that we somehow have learned this matrix S, and you see that the number of rows is 5, so the same number as the number of nodes here, and the number of columns is 2. So since the number of columns is 2, we know that the output will be a graph that contains just 2 nodes. And you see that the rows sum up to 1, and those are kind of, you can think of that as probabilities that each one of the 5 nodes belongs to the 2 new nodes, to the 2 new clusters. And once we have this matrix S, we can just do these matrix multiplications. And this matrix contains the features of the nodes of the new graph. And this matrix contains, is the adjacency matrix of the new graph. And you see that from this graph, we produce that graph that consists just of 2 nodes. This is a weighted graph now. We have weights on the edges. We also have self-loops because the diagonal is not equal, the diagonal values are not equal to 0. And we can add another layer later on and have, in the end, a single node, and we can use the feature vector of the last node to make predictions. Let's now move on to a different topic in graph learning, and this is related to the expressive power of graph neural networks. A question that you might have is, we have 2 graphs that are not identical, they are not isomorphic to each other. If we use the models that I just presented to compute vector representations, will they always produce different vectors for graphs that are not identical? So the answer here is no. This is a counterexample. So you see these two graphs, G1 and G2, they consist of 6 nodes, and they are both regular graphs, so all nodes have degree equal to 2. And if you feed those two graphs to the models that I presented before, the representations that will be generated will be identical for those two graphs, even though those two graphs are different from each other. And in fact, it has been shown that the standard message passing neural networks, they are at most as powerful as the Weisfer-Lehmann test of isomorphism. So this is a heuristic algorithm that was proposed many, many years ago, and it can solve the graph isomorphism problem for many classes of graphs, but there are some graphs for which it fails, like those two ones that you can see on the slide. So message passing models, the simple message passing models, they can be at most as powerful as the Weisfer and Lehmann test. And in fact, we can build some model which can achieve this expressive power if those three functions, aggregate, combine, and read out, they are all injective. And injective, roughly speaking, it means that if we feed different inputs to those functions, we get different outputs. So the question then is, are the commonly employed functions like the mean, the max, the mean, the max, and the sum, are they injective or not for functions over multisets? It turns out that the mean and max functions are not actually injective. And these are some counterexamples that show that these functions fail to learn injective representations over multisets. But on the other hand, the sum function, it can represent injective functions over multisets in case there are some constraints that the input domain is countable, but in general, the sum aggregator can be injective, so we can have models that are at most that can be are as powerful as the WL test. And in fact, one model that, if proper weights are learned, is that powerful is the graph isomorphism network. And you can see the two steps of the model. So this is the formula for the message passing layers, how we learn new node representations. And you see that we use the sum function here. And this is the readout function. From the node representations, we compute a graph representation. And again, you see that we use the sum function. So in both cases, we use the sum aggregator. And if proper weights are learned, so if we learn proper weights for the MLP, then this model can be as powerful as the Weisfer and Lehmann test. Okay, but the example that I showed you before, so this example, you might say that these graphs are not realistic, so in practice we never we will never have that kind of graphs. So there are some regular patterns in these graphs. But it turns out that there are some graphs in the field of chemoinformatics, like these two chemical compounds, that cannot be distinguished by the Weisfer and Lehmann test. So if we feed those two graphs to the Weisfer and Lehmann test, it will fail to say that they are not isomorphic to each other. So this is why people have started working on the expressive power of GNNs recently, and this is a very active field of research. And here I list some approaches that people use to develop more powerful models. And one approach is to, instead of performing message passing between nodes, to perform message passing between subsets of nodes. Another approach is to extract subgraphs from a given graph, then compute representations for the subgraphs and somehow combine those representations. We can use extended neighborhoods. So instead of aggregating the representations of the neighbors, we can aggregate representations of paths, for instance, emanating from the nodes. We can consider all permutations of nodes. and another approach is to utilize invariant and equivariant linear layers. And I will just briefly discuss two of those directions. So perhaps the simplest approach to create more powerful nodes is to consider all possible permutations of nodes. So there is a model called relational pooling that is built on this idea, and you see here how the graph representations are produced. And the idea is that we assign unique identifiers to the nodes, and then we consider all permutations of those identifiers. However, the number of permutations is n factorial, so it's very large even if the size of the graph is small. Here, where we have 3 nodes, we have 3 factorial, which is 6 different graphs in total. So we need to feed those graphs to some GNN model like the graph isomorphism network. This will give us a feature vector for each one of those graphs. We sum those vectors and we get the final representation. So in fact, this model can even solve, if proper weights are learned, it can even solve the graph isomorphism problem. But it's not in practice, like we cannot use it in practical application. Its computational time is prohibitive. And people resort usually to approximation methods. And as I said before, another idea to create more powerful models is to extract subgraphs from a given graph. Here you see we have this graph, and we somehow decompose this into a set consisting of subgraphs extracted from this graph. And once we have computed, then we can we need to embed this set of subgraphs into some vector. Here there are 2 challenges. How to extract subgraphs from a given graph is the first challenge. And the second is how to map this set of subgraphs into a vector. So for the first challenge, there are different strategies that have been proposed. For instance, edge-deleted subgraphs where we remove one edge at a time. Node-deleted subgraphs where we remove one node at a time. And this is a third strategy, Go networks, where we extract subgraphs that are rooted at the different nodes. So you see that these are the roots of the different subgraphs. And for the second challenge, one simple approach we could follow is to feed each one of those subgraphs to a graph neural network. Then we obtain a vector for each one of them. So from a set of subgraphs, we now have a set of vectors. And there exists a model called deep sets, which is designed for sets, and it's known to be universal in case the input domain is countable. And this can give us a final representation for the input graph. And there are some examples of graphs that can be like non-isomorphic graphs that can be distinguished by such kind of models, while these graphs cannot be distinguished by the Weisfer and Lyman test of isomorphism. I will now discuss a bit about graph transformers. So transformers are very popular in computer vision and in natural language processing. Professor Androutsopoulos, the previous speaker, briefly talked about the architecture. He didn't go into details about the attention coefficients. I won't go either. But in the case of graphs, one problem that we have is that the vanilla transformer does not take into account the structure of the graph. So if we just use a transformer, we lose the information about the connectivity of the graph and of other structural properties of the nodes. So some recent works, they have proposed models that somehow modify the vanilla transformer and take those properties into account. And a recent model called Graphomer, it uses a learnable vector which somehow captures the importance of the node, and it adds this vector to the initial features of the nodes. So here, this vector depends on the degree of the node, and we expect that in most cases, nodes with high degree are more important than nodes with low degree. So this can be learned by the model based on the current problem, on the current setup. And also, this model introduces this scalar into the formula that computes the attention coefficients. And in fact, this phi here, B is a vector and phi is an index to that vector. And phi computes the shortest path distance between the two nodes, nodes I and J. So in most applications, we expect that nodes that are close to each other, a node depends more on nodes that are close to the node than on nodes that are farther away. So we expect that B will take large values if phi is small, and it will take small values if phi is large. But again, it also depends on the task at hand. For a given task, we might see something different. One problem with one limitation of graph transformers is their computational complexity. So the complexity is quadratic to the number of nodes of the graph. So for some social networks which are very large, like thousands of nodes or millions of nodes, of course we cannot compute this matrix of attention coefficients because it doesn't fit into the memory of conventional machines. But we can apply these models to molecules because molecules are typically very small graphs. And I will finally I will present some experiments on two molecular property prediction data sets. So these, the first data set, zinc, it's a subset of a larger data set that contains 250,000 molecules. So this subset consists just of 12,000. And this is a regression task, and what we need to predict is the constrained solubility of molecules, and we need this value for drug design applications. And the second data set, it's contained in the Open Graph Benchmark collection. This is a collection of large-scale data sets for graph learning algorithms. This data set contains more than 40,000 molecules, and the task here is a binary classification. We need to predict whether a molecule inhibits HIV virus replication or not. And so these are the results on the zinc data set. We report mean absolute error here, so the smaller the better. And you see, I've already presented some of these models, and you see that the simpler models like GCN, GAT, and GIN, they are outperformed by more powerful models like PPGN, CIN, ESAAN, PathNN, and so on. And you can also see that the graph transformers of this model is competitive with the more expressive models. It's the achieved mean absolute error is close to that of the best performing models. And this is my last slide, some like the results on the graph classification data set. Here, the higher the better. And again, the patterns in this table are similar to the ones of the previous one. You see that the first two models, which are very simple, they cannot compete with the rest of the models. And we have some like more powerful models on the bottom of the table. And again, once again, CIN is the best performing method, and the graph transformer, once again, in this case, it's the second to best method. Okay, so thanks a lot for your attention.
We have time for questions.
Hello, thank you for your representation. I have two questions. If I have understood right, the models like GCN or G attention net, is about to get some embeddings of the graph, right?
Of the nodes, and then we can also add the readout function to get an embedding of the entire graph.
Okay, so it is like the masking for pre-training BERT, like we saw before.
I wouldn't say it's similar. It's like you have a classification or regression task, but you need to classify nodes or graphs this time, not documents or words or...
No, I mean that it is only for the prior. We want to take the prior, I mean the pre-knowledge of the model. And then we will use it, we will add a head for fine-tuning in another task.
We do this in the case of molecules. We don't do this generally for graphs because graphs from different domains are very different from each other. So if we've learned something for graphs from social network, we cannot generalize to graphs from chemoinformatics. So we usually focus on a specific domain and learn pre-trained models for graphs from that domain. And typically for molecules, for proteins, to be honest, I'm not aware of any other areas where we learn pre-trained models for graphs.
Okay, and the second question is about Graphomer. I want to know what is the actual input. I mean that we have already run the GCN, for example, and take the embeddings and
No, we directly feed the graph to Graphomer.
Okay.
So we have some initial node features. So we have these vectors. Initially, these are the original node features. And we just do this computation, and we have also this scalar here, which somehow takes into account the structure of the graph.
Okay, but
So
how we get the initial features of the nodes?
These are usually given to us. For instance, for molecules, there are some properties of the atoms. In social networks, we might have some features for the users like sex or, I don't know, stuff like that. If we don't have such kind of features, then we can either create some random features, or we can create some features from the local neighborhood of the node. So one feature could be the degree of the node, another feature could be the number of triangles in which the node participates, and features like these structural features.
Mm-hmm. And that's why I asked before if we have run already for example, the message passing method for getting the features from the nodes.
No, we have some initial features,
Okay.
and then based on these features, in a sense, we transform those features using the message passing layer.
Mm-hmm. Okay, thank you.
Thank you.
I would like to ask how you actually use the graph theory in practice to solve a problem. As I understood, you get a problem which could possibly modeled in a form of graph, and then you write in programming language to solve, to make it to have an answer on the problem. For example, you mentioned in the beginning social network. It's it could be modeled in the form of graph. Yeah. Is it how it's working? I'm trying to understand how you use graphs to solve a specific practical problem.
Yeah, we need to have some labels. So class labels in the case of classification problems, some target real values for regression problems. Then it's like similar to other neural networks. So we can use any package that we typically use for other models like PyTorch, or if I'm not sure if this is what you asked for.
Yeah, I mean, yeah, I say program.
And there are even packages that implement those layers that I presented.
Okay.
There is a PyTorch geometric package, which gives implementations of the GCN layer or of the GAT layer and so on. Yeah, so we just add those layers to the model like we add the conventional layers like CNN layers or dense layers in other cases.
So there is a specific software package which...
Yeah.
Okay.
There is PyTorch Geometric, and also there are other packages, and they are compatible with PyTorch or with TensorFlow. It depends on the package, or with both.
Yeah, they are Python libraries.
Yeah.
Like Python. Okay. This is what I wanted to ask. Thanks.
Hello. I have two questions, probably one. The first, I think you answered already. You mentioned that we use these neural networks, the graph neural networks, mainly for chemoinformatics. So my question is there some cutoff, a level that you can't go above? I think you mentioned you can represent proteins like this.
Yeah.
Is there some size of how complex can this protein can be, if there is a size limitation?
If you mean in terms of number of nodes, there is no. For like the message passing models, they are very efficient. So the time complexity is linear to the number of nodes, or linear to the number of edges, I'm sorry. So we can apply the message passing models to any graph, I would say, not like billions of or trillions of nodes, but we can handle like millions of nodes on a conventional machine. For
when
graph
you say
transform,
conventional machine,
like 64 gigabytes of RAM, for instance, or a GPU that contains, I don't know, 24 gigabytes of memory.
that's very conventional, okay? That's like a gaming PC.
Yeah.
A little bit more, yeah, okay, but it's not something extraordinary, okay?
But we can't use graph transformers when we have that large graphs. Even for proteins, we might have some problem, because for graph transformers, the complexity is quadratic to the number of nodes. So in that case, we might have some problem with memory if we use those instead of message passing models.
Okay. Now I want to make it more complex. Can you, let me rephrase that. In proteins, we care a lot about protein-protein interaction. If I represent one protein as one graphic model and another protein as another graphic model, as another graph, can we see an interaction between them? Can we add them? Can we do something that?
We could have a hierarchical graph. You mean that we can represent its protein as a graph based on the 3D structure of the protein, and then we have another network that captures the interactions between proteins, right?
No, I'm not asking for a specific. I'm asking if there is any kind of solution. I'm not asking if this is the solution. If there is any kind of solution, we represent one protein, protein B, protein A, as a graphic model, and protein B as another graphic model. Can we, and I want to study their interaction. Can we use that? Can we
Yeah,
I don't know, maybe...
Yeah, we could use that GNN to get some representations for the two proteins. But then we need to have some training data to know which proteins interact with which other proteins, so such that we can train the model. And once we can train, we can. One simple approach is the one you mentioned, to just compute the sum of the feature vectors of the two proteins, or some other. There are other ways to combine them, like element-wise product, or there are even more complex approaches. But we need to have some training data.
That's for sure. You need training data. We can provide that through biology, but I'm asking, the idea is that I know for protein A and protein B that they interact, and I want to know about similar proteins, if they interact, if they still interact or not. And from
I
my
think-
understanding is that we can use that.
Yeah, we need to have a set of candidate proteins. If we have such a set, we could compute some representation that combines the two proteins and then make some prediction.
Yeah, thank you.